Hello. Once upon a time, into exciting locations, Singapore and then Hong Kong, I delivered a talk titled My Biases Against Every Consensus Protocol That Is Not Nakamoto Consensus. I chose the word bias for a reason. A professor at my alma mater, Zhang Yefu, has this great line: a PhD equips one to convince others of their biases. How boring a person would be without any biases. And that stuck with me. In that talk, I took on 5 types of consensus protocols that claim to improve Nakamoto consensus. All my arguments were drawn from academic publications, mostly my own. At the end of the talk, I introduced the vulnerabilities of the Ethereum consensus protocol. Sadly, those weren't my own findings. So I told the audience that I was working on several papers attacking other claims that the UTXO model lacks expressiveness as it only supports basic token transfer. But hold on a second. In recent years, a realization has dawned on us that Ethereum has 2 major pain points that are proving extremely difficult to fix. The first one is lack of parallelizability. Ethereum operates as a single-lane highway that can only process 1 transaction at a time. And this performance bottleneck is driving Ethereum's centralization. The root cause of this issue lies in how transactions depend on each other. In Ethereum, racing transactions have to wait for each other's output values in order to process. And 60% of transactions are racing, that they depend on each other because they share dependencies. So you have to wait for the number. In contrast, in the UTXO model, even when a transaction relies on another, it doesn't need to wait for the numerical value because it only relies on the validity of the previous transaction. Therefore, transactions can be parallelized arbitrarily. The second pain point is the MEV attack, where the attackers inject transactions before and or after honest transactions or reorder honest transactions. This attack has caused a total loss of $676 million in its first 3 years, and the number is still on the rise. What's even worse is that it motivates the PBS architecture, which leads to Ethereum's centralization. Nowadays, the 2 largest builders of Ethereum decides 97% of all Ethereum blocks, which is another problem I don't have time to dig into. Because of these 2 pain points, the community has a growing sentiment that the UTXO model is superior. But is that a responsible argument? We need to think deeper and more rigorously about this argument. Previous studies analyze the ledger model by comparing the 2 blockchains directly. We summarize their results into 8 characteristics. However, we feel that, and it's trivial to see which blockchain performs better at which characteristics. However, we feel that these analyses are not complete. Why? For starters, these characteristics are not equally important. Some disadvantages are easily fixed so that they don't feel to touch on the essence of the ledger model, which can be further traced back to existing analysis conflate the ledger models with their implementations. People mistakenly equate the UTXO model with Bitcoin and the account model with Ethereum. The underlying reason is that there's no formal definitions of the UTXO and account models. Therefore, in these studies, we would like to answer the following 4 questions. First, how should we define UTXO and account models? Second, which characteristics are determined by the ledger model and which are influenced by the implementation? Third, do these 2 encompass the full spectrum? Fourth, which ledger model is inherently better? Here's our technical roadmap. Our key intuition is to define the UTXO and account models as the core design choices of Bitcoins and Ethereums, their earliest blockchains. So we start by listing Bitcoins and Ethereum's implementation fields. How do they implement their states and transactions? And then we match these fields by their functionalities or purposes to get a series of conceptual fields. As we are most interested in the differences between these two models, we extract the differences as 7 attributes. And then we select choose the most essential attributes, whose criteria will be explained later, and get 2 intrinsic attributes. Once we get the intrinsic attributes, everything becomes crystal clear. We answer 3 of the 4 questions in a single slide. Here's Bitcoin's implementation fields. A Bitcoin transaction destroys some existing UTXOs and creates some new. Things are quite different in Ethereum. Ethereum has 2 types of accounts. The externally owned account, EOS for short, and contract account, CS for short. The first one can initiate transactions. The second one can host code and data. Here are Ethereum's implementation fields. By matching these fields, we get these conceptual fields. However, this is not enough because these fields are not equally important. For example, the amount field is equivalent in both blockchains. It doesn't matter whether you call it value or balance. Also, we don't truly care how each blockchain protects against the replay attack. As long as the attack is prevented, there is no further implication. So we abstracted and shortened the table into this one, which consists of 7 attributes, which reflects the differences between the 2 blockchains. To further narrow down the selection, we rely on 2 heuristics to select the intrinsic attributes. The first one is exclusiveness, which means an intrinsic attribute must be independent of another. The second one is immutability. The underlying intuition behind this is that if for a certain attribute, the weaker model can be adapted to the stronger model via simple technical modifications, then it is not intrinsic. However, if such technical modification would invalidate historical transactions, it is intrinsic. 2 attributes survive this screening process. The first one is identifier. Bitcoin's identifier is consumable, as each UTXO can be only accessed once. Ethereum's identifier is persistent. Both types are persistent. The second one is the transaction structure. The complete transaction structure is STX S prime, which represents old state, transaction, and the new state. Bitcoin omits the transition, which retaining only existing UTXOs and new UTXOs. It's like a cake. The procedure is implicit and the outcome is explicit. Ethereum omits the output state, which translates to the from address and what needs to be done. It resembles a recipe, where the procedure is explicit and the outcome is implicit. The output state is unknown until the transaction is executed. Now we have arrived at the most important slide in this presentation. It is evident why these 2 attributes are independent and immutable, which gives us the definition of the UTXO and account model. The UTXO model is a ledger model with a consumable identifier and a transaction structure S prime. The account model is a ledger model with a persistent identifier and a transaction structure STX. Given that these 2 intrinsic attributes are orthogonal or independent, it's natural to combine them, to recombine them to get 2 new ledger models. We call them the token model and the balance model. Now let's revisit the characteristics to see which ones are intrinsic, are directly related to the intrinsic attributes. The privacy and the parallelizability advantages of Bitcoin can be ascribed to its identifier, to its consumable identifier. And the determinism and on-chain execution advantages can be attributed to its transaction structure. Moreover, we find that these characteristics are not independent of each other. For example, determinism implies parallelizability, which further validate that our bottom-up approach is more rigorous and systematic than the characteristic-based approach. Analyzing these characteristics gives us an observation that could be infuriating to some. The UTXO model outperforms the account model in all intrinsic characteristics. I still have so much to say about ledger model, but for now, let's shift our focus to the second study called United We Fail, Divided We Stand, Measuring and Attacking the Ethereum Global Network. Let's start from the very basics of the peer-to-peer network. This node discovery model covers all peer-to-peer network. In the network, each node holds a routing table, which stores the routing information of other nodes, like IP addresses, TCP ports, UDP ports. When a new node joins the network, it will contact the boot nodes, whose routing information is hard-coded in the source code for existing nodes' routing information. We call this request message find node. Now that the node's routing table is no longer empty, it will contact more nodes and ask for more nodes' routing information. And the process repeats itself. Moreover, the node will also try to establish application layer connection to other node via a handshake protocol. This process also repeats itself until the number of application layer connection reaches 16. As long as the node has successfully established some application layer connection, the node can exchange blocks, transactions, and other messages related to the service. And we call it successfully joining the network. So what's so special about Ethereum Global Network? In a typical peer-to-peer network, it hosts one service. The Bitcoin network hosts Bitcoin, the BitTorrent network hosts BitTorrent. Plain and simple. One office for one company. The Ethereum network hosts around 2,000 services. It's like 2,000 different companies working in the same giant office, and each new employee is randomly assigned a desk. I asked Google Gemini's opinion about this, and here's what it outputs. It says this unique architecture allows for incredible innovation and flexibility. New services can be launched and scaled rapidly without the need for building separate infrastructure. It's a testament to the power of decentralized technology, where the boundaries between different services blur, and the possibilities are truly limitless. So what's the potential benefits? What are the potential benefits? By joining the same network, the new project can maximize code reuse, which saves them some development costs. And they can piggyback on other services' boot nodes, which reduce deployment costs. And they can enjoy higher node discovery efficiency because more copies of their routing information means they are easier to find. They can have better attack resistance because a larger pool dilutes the attacker's influence. And they can have better potential for interoperability. However, 3 of these 5 potential benefits do not warrant any further technical investigation, because maximized code reuse has no direct external impact. Piggyback on the boot nodes has marginal economic gain and huge security cost. And there's no concrete plan for interoperability. So in this study, we dive into the other 2 potential benefits. Our technical work comprises of 3 components. First, we measured the scale, nodes uptime, service distribution of Ethereum Global Network, also the service distribution in DHTs. Second, we assess the node discovery efficiency by tallying the number of find node messages and handshake requests for each successful outgoing connection in both EGN and in a dedicated network setting. Third, we analyze the security by evaluating the impact of a weakest DHT pollution attack, also in both EGN and in dedicated networks. Here's the service distribution. Ethereum mainnet node consists only 30% of all the network nodes. And an interesting discovery is that there are hundreds of nodes that are operating on some old Ethereum forks. Here is the service distribution in those DHTs. The results are truly worrying because for most public nodes, they have less than 20% of nodes of their own service in their DHTs. Things are slightly better in boot nodes, but this is not because the boot nodes gave priority to nodes of their same service, but because when a new node joins the network, it will first contact the boot nodes, which means this number can be easily manipulated. Here's the efficiency results. It can be seen that for every successful application layer connection, a node needs to try at least 1,000 or sometimes tens of thousands of times. In contrast, in dedicated network, the bandwidth, latency, and number of messages would save 50% to 98.3%, with the number varying according to different services and different estimation methods. A stark contrast emerges when you look at the number of Bitcoin. In Bitcoin, every 4 handshakes lead to a successful connection. Now for security, we evaluate against the weakest attacker. The number of attacker nodes is less than 1% of the network scale, and the attacker exploit no protocol or implementation flaws. The only things the attacker do is to send ping messages to honest nodes and answer fan node with attacker nodes. Such a weak attacker will not be able to cause any actual damage in any other peer-to-peer network. We only display a single point in our results. With 300 attacker nodes in EGN, the percentage of same service peers in the nodes DHTs and the percentage of handshake success rate drops to 0. On average, 583 nodes are permanently partitioned from the rest of the network into 20 connected components. However, in dedicated networks, it performs relatively stable and can easily defend against the attacks. The underlying reason is that if your DHT is composed fully of your same service nodes, honest nodes can easily find each other and connect, which safeguard the network. What about the potential benefits? In reality, a larger network guarantees improved data availability only if the data itself becomes more accessible. And it dilutes attacker resources if it maintains robust internal connectivity. If your castle is made of sand, no matter how big it is, it can be washed away. Let's draw some insights from these two studies. When designing a system, we must strike an intricate balance to do the right thing. We must avoid under-engineering. Some blockchain projects reuse each other's source code and even share their infrastructure, which is highly risky. Also, we must avoid over-engineering. Ethereum, for instance, often reinvents the wheel. While innovation is crucial, sometimes the simplest solution is already the best solution. If you make it too complicated, no matter how beautiful the design is, a single spark can bring it down. Ethereum's design aims to maximize expressiveness. In pursuit of external visibility, it sacrifices determinism. With external visibility means the ability to access without destroying external code or data. It sacrifices determinism, hence security, and parallelizability, hence efficiency. On the other hand, Cardano's EUTXO model gives up external visibility in exchange for determinism and parallelizability. A question arises. Can we have our cake and eat it too? Is there a ledger model that is fully expressive, deterministic, and parallelizable? Our next paper will introduce this model to academia. I hope you are as intriguing as this topic as I do. That's all. Thank you.